Okay, today is the final lecture on shear. So within this lecture, we'll be covering to the end of the course book. So that means that we'll be having a look at example number 5. We'll also be having a look at example number 6, which will take you to the end. After this, there's the problem sheets. So solutions you can look through if you need to, but I'll just point out that one gives students some difficulty at first. So I've got some notes on that one there. This question here always gives students difficulty. So I've got a set of notes on that one there in the Dropbox. If we go further along through these here, you will find the past exam questions. Again, solutions that you can find, and then if we have enough time, we'll go through some of the concepts explained by the students. So let's have a look first, back to here. So we're now here going to be talking more about shear flow. So if we've got So before I do that, if you did want one of these, I've been communicating with the technicians in the MDLS, and I think they've arranged for you either to arrange for them to be couriered to your house, if you want to, or alternatively you can go and do a click and collect, which is what the students did last year. So if you wanted one of these, if you did find them helpful, a lot of students find them helpful initially, but then they say they're quite happy with the models shown under the camera here. But if you actually did want one of these, then just contact Paul, and I think he's already sent an email out. So we're going to be talking about shear in thin-walled open sections. So let's have a look at this here first, which is shear in thin-walled open sections. And using thin-wall theory, you could sort of imagine that if this became thinner and thinner and thinner, then we could ignore the transverse stress distribution. So for the flange, the transverse stress distribution would be in that direction. And then for this one here, it would be in that direction. So we're just ignoring any variation in shear over the thickness. So for the flange, if we drew out a section like that, so I'm obviously drawing it out very thick. So thin-wall theory isn't applicable when something is thick. But say you've got this case here, if it was thick, then the stress distribution in the flange may look something like that, with that being a parabolic shape. But if you had a section that was very thin in comparison, so I'll just try to draw out exactly the same dimensions, but just imagine that it was much thinner. Okay, so we've got that like there. Okay, so there will be a stress distribution. There will be a stress distribution which would be parabolic, if you could work that out. But I think it might be quite reasonable to say that you can ignore the variation in this direction. After all, you've got the air here, you've got the atmosphere here. So the stress distribution, or the variation of stress from the top to the bottom, is going to be very, very small. Now, when it comes to carrying load, so you've got your thin-walled section like there. So if that is under a force there, or that's under a force there, so let's just say just arbitrarily 10 kilonewtons, and arbitrarily just say that's going to be 10 kilonewtons there. One of the things that we'll realize at the end of this is that the shear is almost going to be all carried by the web. So there's going to be very, very little shear carried by the flange. So it might be a reasonable assumption to say that if the section is very, very, very thin in compared with the overall dimensions, that the variation of stress in that direction, so that's the flange blown up, so there is a variation of shear stress which is parabolic, tau. So there is indeed a variation of shear distribution, but we might just say we can ignore that and just say that's 0 kilonewtons per millimeter squared. So that, of course, is an assumption, and the assumption may not be that accurate when you've got a very thick section, but the thinner and thinner and thinner you make the section in proportion to the overall dimensions, this assumption that there's no transverse stress distribution through there, or there's no variation of stress because up here is the air, so there has to be 0 stress there on the top surface. Down here, again, the air, so there has to be 0 stress down there. And that, if that's really, really, really thin, say 1 millimeters, like the the kit that I brought in the first lecture to show a channel, that shows a channel section that might have just been 1 millimeter thick, I think it's very, very reasonable to be able to say we can simplify our calculations a lot by saying that the stress in the transverse direction for the flange, or the stress in that direction there for the web, or the variation of stress in the web is going to be completely negligible. Okay, through the thickness, of course. What we'll cover later on, let's just get rid of that. So I've talked about the assumption that we're going to be making just to simplify the calculations, which is the transverse stress distribution being 0. Now, if you had a channel section like there, which could be like that, so I'll draw the thickness there just so you can see it, and maybe I'll draw another channel section like here on that side there. So with these thin sections, you might be making 2 channel sections, putting them back to back to make it like an I-beam, which we've seen there. You know, that can be bolted or whatever, but I'll just like to focus on this idea of the channel section first. So what we're saying is there's no shear distribution down there, but there will be some shear stresses going down here in the web. So you can imagine you've got that. I stick some load on. I think even with a ruler, even with a ruler or a piece of paper, you could actually physically feel that it's this bit that's going to be taking all of the stress, and these 2 things here are not going to be taking any of the vertical stress. But here comes the here comes the interesting bit, is that even though there's no variation of vertical shear distribution through the thickness, because it's a thin piece of, it's almost a thin piece of paper, so you could feel that there's going to be no variation of shear stress through the thickness. It doesn't mean that there isn't a horizontal shear stress. So down here you can see there's a horizontal shear stress. So if this is the variation of vertical shear, and the variation of vertical shear here is 0, there is actually a variation of horizontal shear going along there. Okay. And there is a variation of horizontal shear going in that direction there. And this is where the term shear flow comes in, because it's quite nice to be able to, you could sort of rationalize to yourself, it's flowing like water. This doesn't always work, but you could rationalize to yourself and say, it's flowing like water, so the shear flow must be going round like there. Okay, so there is a shear flow going round the section like there under the action of the vertical force. Okay, so this well, if you got this example, if you got my sheet of paper which I put on one of the pages and took it out and folded it, you can probably see that I've annotated it a bit, and I've shown the vertical shear down here. That's all fine. So, and you can probably see I might have done some scaling of the arrows, so that arrow should be smaller than that arrow, and this arrow should be bigger than that arrow down there. So if it was all vertical, so hold that there and put it down, that would be, might be the parabolic distribution. But hey, what happens if we make a fold make another fold, you've got a channel section, there is still that distribution of shear along here, which I've drawn, okay? Which, because it's now being folded, so before it was all vertical, as you can see, but because I've made a fold, it doesn't mean that it's disappeared, and it's still there. So there is vertical, there is a horizontal shear distribution along going in that direction, which is going to want to kick this out here. And there is going to be one in that direction, which is going to want to kick that out there. So in terms of forces, let's say that's the that's the shear distribution going down in the web. And if I integrate it, that one, I'll probably get the load going down there. But there is also a shear distribution, which in this case here is horizontal in the direction of the arrows, and that's going in these two directions like there. So we all know that Lucas has covered all this before, so this is just really revision, but I'm pretty sure that Lucas would have explained this before, and this is where we end up with the concept of shear flow. And shear flow, simplification, no transverse stress distribution, just ignore that in the calculations and we can go ahead with some easier calculations. So now down here, of course, that's the stress, okay, that's the vertical shear stress, and then that one is just an axis either going up or down. Let's just say it's going up, might be, just in case that confuses people. So it doesn't really matter which the axis goes, it just shows whereabouts on the web you are of the section. Now, if the thickness of this thing here was 1 millimeter, if the thickness was 1 millimeter, okay, so that means if that, we just imagine that that thickness is going to be 1 millimeter and that thickness is going to be 1 millimeter. So if the thickness is equal to 1 millimeter, then tau actually equals Q, okay? So Q and tau, so I think everyone is quite happy with tau being in units of newtons per millimeter squared. What's the difference between tau and Q? Q divided by thickness is equal to tau. Okay. So they're effectively the same, just related by the thickness. So Q is the shear flow. So units of Q are obviously newtons per millimeter. So I believe that it's what's known as attraction. And to get, so we're going to be calculating Q, which is attraction, newtons per millimeter. And if you wanted to convert Q into tau, you just divide it by the thickness and suddenly you've got the stress. So here I'm showing it with an arrow, a single arrow, and of course if it had been a stress that I'm showing, and I zoomed in there, I may be showing arrows like that to signify the stress. So instead of showing the shear stress going downwards, I'm getting rid of my thickness, which is here, and turning it into what I call a traction. And to turn the traction into the stress, you just divide by the thickness. Okay, so hope that all makes sense. So I'll get rid of that, just in case it gets a bit confusing. Now, it's quite nice to be able to think of it as a flow. So you can see you're flowing, if this was a pipe, it's flowing all the way down. And then you don't need to say, is the shear flow going in that direction or in that direction, or is this one going in that direction or that direction? You don't really get confused because you can use this little trick and just show it going round. So that's why it's called a flow or a shear flow. So let's have a look at some other objects like this one here. Okay, so if you're okay with that, all the vertical, so I'll call it shear flow, all the shear flow is now going through here down to a small value there. And if you're okay with the channel section, you're probably okay with the idea that that flow would be the horizontal shear is going in that direction there. And then what happens on the other side, you can see it sort of flowing. So you might say, okay, let's draw the flow, and then draw the flow going out here. Okay, so it's just something you've got to reason out for yourself. Now remember that when you've got something like that, a channel section, sorry, an I section, which we've got up here, if you've got something like an I section, and you say, where's the centroid? You'll probably say the centroid is there. And then you'll probably say there's a line of symmetry going through there. So the centroid is at that point. So in this one here, centroid is at that position. And what's also at that position is what's called the shear center. Now, in this case here of the channel section, where's the shear center? We'll be calculating the shear center just by taking equilibrium about a point. So that is effectively a force, traction, multiply that by that length. You'll be able to turn that by some integrals into a force. So you can get a force. You can turn the stress into shear flow. You can turn the shear flow into a force. So you end up with two forces in the flanges going down, causing a couple. And you can probably feel that's going to cause a section to twist. We don't like sections twisting under torsion because that's not particularly good. If the load was going through down there, as you can see, then the section is going to want to twist. But if the load was going through, say, this point here with a distance E away, and we'll call that the shear center, and we'll be seeing how we can calculate the position of the shear center later on. If that position, by calculating that position relative to the equilibrium of these, which is wanting to cause the couple, if the vertical force is applied through that shear center, 10 kilonewtons, if any load is applied through that shear center, then this section will not want to twist. That's a bit of a tricky concept. Some students in the past have written out an explanation for the shear center showing it, depending on where you pull it. So if you pull it at the shear center there, you can see that the section does not want to twist after the load has been applied. And a student here has given some explanation as to the position of the shear center. So I've noticed in that student explanation that they've actually put the force going in that direction, which would mean that will go in that direction, which would mean that will go in that direction. So everything is reversed from what I've shown. Just remember that at the start of the first lecture when we did that, and I said take a cut. So you take a cut one side, then the shear is that side of the cut, and on the other side of the cut is up. So hope you all remember that. So it doesn't really matter whether the shear is going there or the shear is going there. It's just looking at either side of a cut. So don't get confused if sometimes the directions of the forces have changed or the direction of the shear flow has changed. Just remember that you're moving your way around the section. Okay, so I'll get rid of that. So I've now introduced this concept of the shear flow, which is this horizontal shear stress, which would have been there if the section, had been like there, then this would be the same as the vertical one. So if you imagine that that had been turned around, so turning it round until it was horizontal, that is the shear Q, and that has now gone in the horizontal direction as a result of me putting this fold in the section. Okay, so you can hopefully see I've drawn out all the shears along here, and hopefully you can see that, and then follow it all the way down, and you can see it going there, tailing up to zero. Okay, So that in a nutshell is what it is. Now, if we talk about a box section, how does the shear flow go with a box section? So if you had a box, like that, so again, Lucas would have covered it. If you had a box section going down like there, and again the load was acting there, hopefully you could reason that the shear flow needs to be in that direction there, downwards, and as we said, that the webs would be taking most of the shear, as we can see there. And then if this is the flow, then hopefully you could reason that the shear flow on the horizontal portion needs to be in the direction of the arrows that I've shown here. Okay, so hopefully that's reasonable. Which means, so it would be going, the shear flow would be going down there, and the shear flow would be going down like there, and that is comparable to half of a channel section. So the concept of the shear flow does need some reasoning, but it is not a bad way of helping you think about things. So let's move on. Shear in a thin-walled open section. Metallic beams, steel, aluminium have walls that are thin compared with the overall cross-section dimensions. Such beams are classified as thin-walled. So we're just pretending that's a thin-walled beam, although I do think that doesn't look particularly thin in my opinion. I think it needs to be a lot more thinner, but then if they drew it a lot thinner, they wouldn't be able to make the point which I'm trying to make here, that the variation of shear in that direction is 0. So that's the point that they're trying to make. So applying our previous reasoning would give a distribution of the vertical shear stress, and these are free surfaces with the air on top and bottom. So if it's thin, yes, there will be if it's thin, yes, there will be a shear stress in the vertical direction for the flange. But it's so small compared to the horizontal one and to the vertical one here, that as an engineer we're quite happy to make the approximation of saying we can ignore it. So the correct procedure or thick wall theory is to take into account this variation, as the element is shown here. The shear stress at the position where the flange is cut off will be given by the equation repeated here for convenience. So the correct procedure using thick wall is to take into account this variation, but we can say we're happy to make an approximation that the variation is 0, and if we're happy to make that approximation, then we don't need to worry about the variation of the shear in the vertical direction as shown here. So all of these in the vertical direction would become 0 by the approximation, by saying it's thin, the air's here, so let's just call it 0. Now, we've talked about that there is a horizontal shear in that direction there, or that direction there, and how do we calculate it? Going back to the original equation, tau is equal to the shear force times the first moment of area divided by the second moment of area of the cross-section times b. The bottom divided by b. S dash refers to the first moment, and b is the flange thickness. And to calculate this horizontal force, so this horizontal force, or the horizontal traction, or the horizontal stresses, so the horizontal shear stresses for a channel section, they're really important, because they're going to want to make the section twist. And for this shape here, they're equal to each other. So here we've got this and this in opposite directions, whereas for this, which I didn't mention before, there's a vertical shear distribution, and then the horizontal ones would be like that. Okay, so the horizontal ones would look like that, but these two cancel each other out, and these two cancel each other out. So there's nothing that's going to want to make the section twist, and hence put this position of the shear center outside of the section. So how do we calculate it? Exactly the same as before. So if I drew that, and if I drew that, and if I drew that, and I said, hey, I want to work out the shear stress or the shear flow at that position, and the shear stress and the shear flow would numerically be exactly the same value if the thickness was equal to 1 millimeter. This one here would be the neutral axis of the section. I want to know what my shear at that position is along down there. So I want to know what is down there. And what do I need to do? I need to go back to this equation here. Then I need to just consider only that bit of the section. Okay, so my horizontal shear force acting in that direction or in the opposite direction if you're on the other side of the cut, doesn't really matter, can be obtained by V, which you know, multiplied by S dash first moment of area of that around that axis divided by second moment of area of the entire section divided by the thickness, in this case here, which would be 1 millimeter. So that B in this case here, I'm just calling it T for the case of the flange. So I'm able to calculate the stress, the horizontal shear stress. I'm therefore able to work out the traction, which helps me take into account if the thickness wasn't exactly 1 millimeter, if it was 2 millimeters or 3 millimeters, I'm still calculating the same value Q. And then from there, I can turn that into a force. Okay, so I hope that's clear. So this one here, calculate shear flow and shear stress distributions in the thin walled I-beam shown in figure 15. So here we've got there. So at this stage, I'll introduce some ideas. So we've talked about the shear flow. Let's imagine that if it was really thin, so let's imagine it was really thin, and my approximations all made sense. So at this junction here, there's going to be something which I'm going to call Q2. So I'll say that the distribution so we know that the distribution of the vertical shear is going to be parabolic. So I'll draw that with a parabolic stress distribution, and let's just put a horizontal portion there. Okay, should be bigger, but okay, so let's just assume it's like that, and I'll just say that that's going to be my triangular distribution of the horizontal shear stress, or the distribution of the shear flow going in that direction. And if that was the shear flow, then area under the triangle is going to be the force acting in the flange when you do your integration. Sorry, let me just make another adjustment, make that a bit bigger. So on the other side of this flange there, and we'll go through the calculation later on, you've also got a triangular distribution, and along down here you've also got a triangular distribution. So if you're wondering why it's triangular, it's because it's all in the same line. Here it's varying, so it's parabolic. Here I think you can work out to yourselves that the horizontal stress is going to be triangular. Going from 0 at the here up to a value there. Now this one here is going to be what I would call Q4, because it's at the neutral axis of the section, and that presumably is well, that presumably is asking you to calculate Q4. Remember, if you wanted the shear stress distribution there, you would just divide Q by the thickness, whatever the thickness happened to be. And hopefully by this stage you will see that why we're more comfortable using Q rather than tau. Okay, but Q and tau are very interchangeable terms, and they're just pretty much the same thing. So what we're going to be saying with this concept of the shear flow is that I'm going to call this Q3. Okay, so Q3 is going to be, if that was the so this is a bit confusing because it shows some thickness, or quite a bit of thickness here. But if you imagine that that T was actually very small, and then I changed the scale just to show the thinness. Remember, this assumption only works for thin when the profile is thin. Then you could probably see that everything would meet at that point. Everything would meet at that point there. And we've got this Q3, and the shear flow in the flange, I'm going to call that Q1. So I'll call that value Q2, and I'll call that value Q1. Q1 and Q2 are of course the same because of symmetry. And as the section becomes thinner and thinner and thinner, so that they've shown, I'll just emphasize again, they've shown the thickness here, so it looks like there's an overlap between the flange and the web if it all met at that point. But I think you're quite comfortable to assume that the T can become very, very thin, at which case, yes, there will still be an overlap at that position, but we can be talking about the center line and everything may meet there. And the assumption, or what we can say, is that Q3, so Q3 is approximately, Q3 being the flow, is approximately equal to Q1 plus Q2. Or if T and T equal 1 millimeter, then tau 3 is approximately equal to tau 1 plus tau 2. Okay, so hope that makes sense. So what the overall concept of this example is trying to illustrate is that you are able to add Q1 and Q2 together to make Q3, which then makes calculations very easy, because then you would say what's the tau at that point, and the tau at that point is Q plus first moment plus the addition going from here to here. So let's say that Q3 or Q4 is approximately equal to Q3, which is the shear flow starting at that point, plus V, which is the shear force, plus times S dash over I of the whole section, and S dash in this case here would be that portion there. So if I worked out, so that's the neutral axis, and then this is where the flange would have been. So if I work out S dash around the neutral axis, if I work out S dash of this portion here, then I will get my Q4. So you don't need to do it that way. You could just do it the way that you're used to, which would just be like making the cut and seeing up and down. But if you can do it like this or get your head around that, then it becomes a lot faster and you can save time in the exam. So let's move on. So there's a full solution in the Dropbox, of course, and I've indicated Q3 is equal to Q1. So this is a dictated solution where I go through everything, and it's probably an hour to go through the whole thing. If you need to, some of you don't need to. So here I talk about making the cut at that position there, and then you've got the Q's, and you can probably see the equation that can come out quite well. Here you're making the other cut, at that point there, and if t is very thin, then you're able to write out an equation q3, which is approximately q1 plus q2. And then when it comes down to the parabolic one, you can work out an equation for q4, which is just q3 plus the bit extra, as I've just shown. So we talk about the parabolic distribution for the web, and for here you can see it's a linear distribution, and in order to get q4 is quite easy. You just take that blob there, work out the first moment of area of that blob around that axis there, which is just the area of that multiplied by that distance there. So you can work out this area multiplied by that area. You've got your S dash, you know what your V is, you know what the second moment of inertia of the whole section is, and suddenly you've got your value of Q2. Once you've got the value of Q2, it's the same as Q1, so Q3 is Q1 plus Q2, you can see that through the maths, and then Q4 is Q3 plus the bit extra. Set first moment of area of this blob here now, first moment of area of that blob, first moment of area of that blob, which is the area multiplied by that distance, since it's about the neutral axis. Shove that through the rest of the calculation. Shear force multiplied by first moment of area of that section of this blob here, divide by I, and that will give you Q4, which would be Q3 plus that. Okay, so hope that all makes sense. But if it doesn't make sense, what do you do? If it doesn't make sense, read through the notes very carefully. Read through the notes in this excellent textbook very carefully, and hopefully it will make sense. And then go through example 5. So earlier on, we talked about this concept of the shear center. So the shear center for a channel section. So we talked about the concept of the shear center of a channel section, which would be that. And we talked about the distribution of the shear flow going from here to here. And this is just the maths that would show how it can be calculated. So consider a thin wall channel section. Sometimes I'm quite happy, well, most of the time I'm quite happy just to show it like that without even bothering to try to indicate the thickness. I just show it as a line. So introduce a coordinate system. So the neutral axis of the section is obviously going to be there. You can work out the first moment of area of the entire section. Introduce your coordinate system, which X that runs along the flange center lines to the right, so that could be your coordinate system, and the shear stress in the flange as a function of X can be calculated through here. So that's the stress at any point, the shear stress at any point in acting in that direction. Okay. It varies linearly with the largest value of the section, so we would expect the distribution to look like that, whether that is flow, Q, or tau. The tau F varies linearly with X, which is why it's triangular. So it comes out nicely through here, and then the resultant force in the flange due to the shear stress is the integral of the stress over that area multiplied by, I suppose, the area, well, the thickness. No, the area in this case, the tau and the area integrate over the area, and you get that out, where AF is the flange area. Resultant forces in the flange would be exactly the same. So here I've managed to get an F, which they've called VF. Resultant forces in the flange would also be VF, so the bottom flange would be the same. Now, introduce a coordinate system that runs along the center line of the middle of the web. We know that it would vary parabolically because it's the same as what we've done before, and then you've got an expression for tau, which varies from the left-hand side of the web as described. So we've got tau in the web, integrate that to get the force in the web, and to check the calculations, put it back in, and we can see that only the vertical shear force is the vertical shear force is taken by the applied force V. So that has all been explained anyway down here, which I said you could feel. You could feel that from a piece of paper and try to put the force. You could feel that it's all been taken by the web. So the V, the vertical force, is all taken by the web, as the algebra has shown. So the vertical force, it's all been taken by the web down there, and there are these horizontal forces that have been here. So if that's 10 kilonewtons, the web is taking, if we assume the channel section is taking 10 kilonewtons, then that 10 kilonewtons is all being resisted by this vertical shear in the web. So when we do our integral of the web, we're going to get the 10 back. Okay, so they've shown it like that with the flow going in that direction, but as I said, it's the same whether you draw it that way or this way. Makes no difference at all, because everything's it's just whether you're on the left hand side of the cut or the right hand side of the cut. And now we've got algebraic distributions of the force, of the force of the two forces and the force in the web. The force in the web, as I've said, being equal to the vertical force that's been applied to the whole section, or that is the shear force from the shear force diagram. Now, as we've said, this section is going to want to twist. So the section is going to want to twist, and there must be a position where that can be let's get rid of that because it's confusing. It's slightly confusing. So there must be a position here where your load can be applied. So there must be a position where your force can be applied. So here, my force must be applied there. If that was a channel section, just pretend it was. If that was no, that's not going to work. So if that was a channel section, there must be a position. The force could go through here, or it could go through here, or it could go through here. But there is a special place where if the force is applied in the vertical direction, then these two twists, the two twists would cancel each other out. So there's a distance E, which you can now see that can be calculated. There's a distance E, and if the force is applied through here, then that's going to cause a twist, and that's going to cause a twist in the anti-clockwise moment. That is equal to V, so the thing's going to want to twist there. This thing here is going to want to twist there. If the clockwise twist is equal to the anti-clockwise twist, then the section is not going to want to twist. So we can now calculate this position E based on that, and algebraically you can see it comes out as 3b squared t over dt plus 6bt. And this is now shown in figure 18. So this position of the shear center can be calculated. So of course you can apply the vertical force here if you wanted to, but that's going to want to cause a twist anyway. You could apply it here, that's going to want to cause a twist anyway. You could apply it here, that's going to want to cause a twist. You could apply it here, which is going to want to make it twist that way, but there's a magic point known as the shear center for a channel section, and if you apply it through there, then the section doesn't want to twist. And the shear center for an I section is, of course, that position there, so through the two lines of symmetry. But this section here, an I section, is symmetrical about that axis and that axis. This is only symmetrical about this axis, so it stands to reason that the shear center wouldn't be on the line of the web. And so as engineers, we don't like sections twisting, So we would go to a lot of trouble maybe to put a bracket onto this section here, like there, to make sure that where we're applying our force, we're applying the force as close to the shear center as is possible. Otherwise the section may twist. Okay, so that just sends the illustration. And this is what we talked about right at the start, where you can see the shear flow for a box section going around like there with the triangular distributions. You can see the shear flow for a channel section. You can see the shear flow for an I section, for a channel section with a lip, and almost all variety of shapes. The shear center of the angle section would lie there. So the shear center of that would lie there, because you've got your two, because it's symmetrical, the shear center would lie there. The shear center is here, and the shear center here is there. So the only difference between this section and this section is this lip coming down, almost like, I've not done it here, but it's like you could make another fold. And then you would have a lip section. Okay. So, examples of shear flow in your thin wall sections. So, example number 6. So, we've just covered the case of a channel section, which I've drawn like there, not showing the thickness, and we've just been able to work out algebraically where that is. Now, what happens if you had a section like there? What happens if you had a section like there? It stands to reason for everything that we've said that the shear center would also be outside of the section, and during these exactly the same maths that we've done before, but this time taking it as part of a radius. So the algebra is a bit different, but the concept is important. The concept is that there is a position known as the shear center. So here is the calculation for that, and I would just say read that in your own time. So you've got exactly the same. You've got the integrals, second moment of inertia, and then the position of the shear center, which can be calculated. And here it works out to be is 4r over pi. Okay, so that's all there. So the concept's the important thing, the concept that there is an E. Don't worry about the algebra. If I have set this question in the exam before, it would be an exploratory question worth 5% of the marks. So whether you're able, even if you're not able to handle the maths for this under an exam situation, it doesn't really matter. It's not going to stop you getting an A. Okay. All right, so now we come on to the problem sheet. Okay, so we come onto the problem sheet. So looking through these, hopefully you can see that these can be done. I'll just draw attention to that one down there. Okay. And this one is the one that students tend to struggle on when they are seeing the concepts for the first time. So these would be the exam questions. So you can see in the past I've taken the exam questions and just a modification of what's in the course book. This one, let's just talk about this one here. So we want to know what the shear, we want to know the shear flow so that we can work out how big the nail needs to be in order to take that shear flow. So with this question here, what you would do, so we've got our equation Q is equal to the shear force multiplied by S dash divided by I. So you can work out the I of the whole section here. That's the neutral axis there. I'm going to take out this bit here. Okay. So I'm going to take out this bit here, which represents that bit there. is going to become my S dash. I'm going to work out the area of that, or the area of that multiplied by that distance to the neutral axis, and that's going to give me my Q. And I would reason out that the flow is going to go out like there. Okay, I would reason out it goes like there. So I'm going to be dividing it by 2 to work out the Q per nail. Okay, so that's just an example of what you might need to reason out, but once you get the hang of it, that's really no problem. This is something that University of Manchester have come up with to illustrate the idea of the shear center. So you can see all that there. Okay. And this is how a student explained the shear center, which I would assume. So if you don't quite understand what the shear center is, maybe if you read that, you might find that it explains the concept, because it was explained by the student after their exams a few years ago. Here we've got the load coming down there, so that's the shear distribution there, and then you can work out the forces, and then you can work out the position of the shear center. So that's for a horizontal I section. This is the example that we just talked about, but before I'm doing a recording, so I can't stop. What do you want?
Because she's going to send it to the bank, I need to call, she said she can't test the shot, I need to call right now.
Yeah.
And the woman will send her email.
Yeah.
You can throw the mat because I'm under that care.
Yeah.
I'm lecturer here.
Are you under recommend now, or are you under?
No, because she said I have no work to try because all my big pride, I'm still considered that, and I just found out it's that.
Yeah, I'll call
I just
recommend.
said that.
Can you give me 5 minutes to finish the lecture? I can't. Yeah, I'll come. So how do you, so with this, there's two variations of the question. So one variation is you've got one plank of wood like there. Okay, so you've got 4 planks of wood and you're putting 4 nails. So that's one variation of the question. And the other variation of the question is that you've got this 1 plank, 2 planks, and then you're doing that one down there and that one doing down there. Okay, and then in this case here the nail goes like so. Okay, so you've got your 2 variations, and then this question will go through the 2 variations. So how do you do it? If you're under this one here and you want to work out the force in each nail, we start with the shear flow, and you might just work out the second moment of area, the first moment of area for your S dash around those cuts, and which would be like that. Or you can treat it one at a time, or for this case here, when you want to work out your S dash, you would work out your S dash based on that. If you were just considering looking at it from the vertical side. So hopefully that explanation showing the plane of the cuts, that would be enough for you to be able to work out the Q, and then work out the spacing in the in-plane direction of the nails. So that's the question, and then this is the one that we just talked about to work out the shear flow in those 2 nails there. So student workings there for you to go through in your own time, or check the Dropbox, and then some stuff that I've extracted from Piazza in the past. And then, as I said, this is the question that seems to trouble students the most. Sorry, not that one there. Sorry, that one's not there. So the one that troubles the students is not here in the course book. So what I would suggest is you go to this one here is the one that troubles the students. So you go to the Dropbox and you'll find that I've got a solution. I've got a solution for this problem. So try, if you think you understand all the concepts, try this problem first, and if you find that you can't do it, go to the Dropbox and look for the solution for that one. Okay, so I think that's enough for me today. So we've completely covered shear, which Lucas has already covered. So we're just recapping what Lucas has covered before, but perhaps this time you need to go through a few more questions than what Lucas would have shown, with a bit more mathematics required. And next, so I would say, you know, the exam of course is going to be an online exam where you will have all the material that you need. So question 1, you've already done that. That would be the slope deflection method, plus the qualitative stuff that you've done through what's it called, ZoraQ. And then question number 2, there will be part A and part B normally. So part A could be on buckling, and then part B could be on shear. So up to this stage here, you've done 2/3 of the material. So if you can cover everything that we've done here, we've covered the material for 2/3 of the exam. And we'll start on the virtual work. Next time.